Welcome to Climbing the Immune Ladder Steps for Success in Science, the IISIAR podcast, where we explore inspiring scientific journeys and the untold stories shaping our research community. We are your hosts. I'm Ira Arosa, a PhD student at the Health Research Institute of Santiago de Compostela, Spain.
And I'm Blandine from University of Virginia in USA.
And in each episode, we dive into conversation with experts in innate immunity, sterile inflammation, autoimmunity, and the mechanisms that drive their resolution, bringing your insights, ideas, and inspiration you won't hear anywhere else. Whether you are listening with your morning coffee or while working at the lab bench, we hope this podcast gives you a fresh perspective on science and the people behind it. Today, we welcome Ira Tabas. He's an American molecular biologist who currently serves as Richard J. Sock Professor and Vice Chair of Research in the Department of Medicine, Professor of Anatomy and Cell Biology at Columbia University in the city of New York, and an endocrinology affiliated with New York Presbyterian Hospital. Ira, thank you for joining us and welcome to the podcast.
You are listening to the If Is Heal podcast, sponsored by Heal Pharmaceutical.
So first of all, could you please briefly introduce yourself and your current role?
Yeah, so I'm Ira Tabas. Been at Columbia for a long time. I direct a research laboratory where we study cellular mechanisms of disease, focusing on the endpoint of cardiometabolic disease, so atherosclerosis and insulin resistance and metabolic liver disease. But we study it at a very deep cellular level, and the ultimate goal of our research is to use that information to come up with new types of therapy. As I said, I direct a laboratory at Columbia, and I also am vice chair of research in the Department of Medicine, focusing on basic translational research. And among the duties in that role is I created and direct a young faculty mentoring program where we mentor career research mentoring for our tenure track faculty. So that's how I spend my day.
Perfect. So could you tell us a bit about your research and what question your life is trying to answer?
Sure. So as I mentioned, we're interested in the cellular basis of disease, and given the prevalence of heart disease, we got interested in atherosclerosis, the disease entity behind the number one killer worldwide. And we got interested in macrophages many years ago. It was at a time when macrophages were beginning to be appreciated as a major player in the pathophysiology of atherosclerosis. And we began by understanding cholesterol metabolism in macrophages, which is highly relevant to atherosclerosis. And that morphed into understanding a very important process in atherosclerosis whereby the macrophages undergo apoptosis, and that contributes to disease progression. And then that led to my lifelong interest, which is what is the fate of those dead cells? And the fate of those dead cells is, in the best possible scenario, they are cleared by other macrophages in a process called efferocytosis. Ferro is the Latin word to carry to the grave or to bury. And so that became a lifelong passion of our laboratory, is to understand mechanisms of efferocytosis and ultimately discovering and appreciating the fact that efferocytosis becomes impaired as atherosclerosis gets worse and worse. And in fact, that impairment of efferocytosis is a major contributor to disease progression. And as a sort of experiment of nature, if you put people on LDL lowering therapy to try to reverse atherosclerosis, and this occurs obviously in the millions of people on statins and other LDL lowering therapy, you can reproduce it in mice, that the defective efferocytosis becomes realivened again. So now the efferocytosis is intact, and that restoration of intact efferocytosis, clearing dead cells in the atherosclerotic lesion, is a major contributor to the improvement of the atherosclerotic lesion in people on LDL lowering therapy, and ultimately resulting in their lower risk for heart disease. We set out to understand, why is efferocytosis such a good thing? And why is it that when it becomes defective, is it such a bad thing? And the obvious answer would be, well, if you don't clear dead cells, those dead cells are going to do bad things. But it turns out that's only part of the reason, and probably not the most important part of the reason. What we and others discovered is that when a macrophage takes up a dead cell through various signaling reactions, it fundamentally reprograms the macrophages to be little factories of a repair process called resolution. And so the reason why efferocytosis is so good when it occurs is it helps the body heal itself in the face of cell death. The reason why it's so bad when it becomes defective is that repair mechanism no longer works well, because the macrophages are not undergoing this essential reprogramming. So we spent many, many years understanding the mechanisms of the reprogramming and the consequences of the reprogramming and why it goes awry. Then realizing that the reason why atherosclerotic cardiovascular disease is still the #1 killer, despite all the advances we've made, is because of the epidemic of obesity. So just about the time that the beneficial effects of statins were kicking in, the benefits stalled, because that was the upswing of the obesity epidemic. And obesity causes many consequences that promote atherosclerosis and ultimately can affect efferocytosis, including insulin resistance, inflammation, dyslipoproteinemia, etc. And we've studied some of that, but our work over the last 10 years has been focused on another detrimental consequence of obesity that contributes to heart disease, namely metabolic liver disease. That used to be called non-alcoholic steatohepatitis, or NASH. It's now called metabolic dysfunction-associated steatohepatitis, or MASH. And MASH is not only the leading cause of liver disease, but it's also a major contributor to atherosclerosis. And so we consider that the sort of deadly dyad, atherosclerosis and MASH, the most common cause of heart disease, the most common cause of liver disease, and the fact that they can crosstalk with each other. We have always been interested in common cellular mechanisms in diseases. So we began several years ago to ask the question whether efferocytosis might be defective in MASH. And that had never been looked at, even though it's well known that in metabolic liver disease, or MASH, hepatocytes die. Nobody had asked what happens to those dead hepatocytes. So flash ahead, and we discovered that there is defective efferocytosis in MASH. It does lead to defective reprogramming, and all of that contributes to the progression of MASH to the most important aspect of the liver disease, which is liver fibrosis. And that involves crosstalk between macrophages and the fibrotic cells called hepatic stellate cells and hepatocytes. And so now our major effort is to continue to dig into mechanism, but we're now at the point where we feel we have enough information to develop novel drug strategies that would be common efferocytosis enhancers to treat atherosclerosis and at the same time treat MASH. Those would be direct benefits on the arterial wall and the liver, but then you get the secondary benefit in theory, because if you treat MASH, you're going to lower a risk factor for atherosclerosis. So that's sort of the idea that we're working on. We formed a small biotech. we have funding, and we're working on that now.
Interesting. So what was there a moment when you decided to focus on immunology?
Well, it was a little bit of a backdoor entrance. My PhD, so I'm an MD PhD, right? So my PhD was in basic cellular biochemistry. It had nothing to do with any disease process or any immunological process. It was looking at glycoprotein biosynthesis. Very important work, but it was not related. And then I came to Columbia to do my internship in medicine. And I quickly became interested in heart disease, particularly heart attacks, right? Atherosclerotic heart disease. And then when it was time to do my postdoctoral fellowship, I read about what was known and not known about atherosclerosis. And it turned out at that time, it was just becoming appreciated that this white blood cell type called a macrophage was playing a very important role that was underappreciated. They knew there were these things called foam cells in atherosclerotic lesions, which turned out to be lipid-loaded macrophages, but people were not even sure what cell type it was. But when I started to enter the field, the role of the macrophage was starting to come to light. And so I was trained as a cell biologist, and so I said, well, I'll adapt a macrophage is my new cell biology interest. And then obviously macrophages are perhaps the key player in innate immunity. And that was really how I got into that. And of course, the work that we've done over the many years, I think has a lot of implications for the general field of innate immunity. But I got into it because macrophages were emerging as a key player in atherosclerosis.
You already answered a bit of this first question, but could you briefly walk us through your trajectory in science?
Yeah. Always a curious person, loved puzzles. My brother was interested in science, my older brother. And so I got interested in science through that and quickly discovered that science was a really good way to solve my desire to solve puzzles. And as a high school student, I, volunteered over the summer in laboratories. And then went to my undergraduate school, which happened to be Tufts University, and needed to earn money. And I got a job as a dishwasher in a basic biology lab, actually studying E. coli. And as I was washing the dishes, I overheard the head of the lab and the people in the lab talking about what they were doing, and I got interested in it. And so I asked the head of the lab, could I, work in the lab as a volunteer in addition to washing dishes? So he said yes. So I did that, and that really piqued my interest in research and basic research. My senior year, I had a formal research project in another lab studying ribosomes, ribosomal RNA. And it was at that point that I need to make a decision where to go after undergraduate school. And for me, the decision was straight graduate school or the new emerging MD PhD programs. And my advisors suggested that the MD PhD programs were probably a good route for me, just because it offered me more options, and yet I would still be able to pursue a bona fide basic PhD. And so I made the decision to do that through a series of events. I decided on Washington University in St. Louis, which was one of the first MD PhD programs, so-called MSTP programs, or medical science training programs that the NIH had set up. So WashU had a wonderful reputation. Went to WashU, did 2 years of medical school, rotating in various labs, and then found a lab that interested me, again, more out of curiosity than anything else, that was studying how sugar groups are put on proteins. And I guess what really attracted me to the lab was the head of the lab, a brilliant scientist, National Academy of Science winner later on by the name of Stuart Kornfeld, actually recently passed away. And he was the type of person I wanted to train under, and fortunately he accepted me in his lab. I did my PhD in that lab. It worked out really well. We made some fundamental discoveries about how sugars are put onto proteins, and it's now sort of like textbook stuff. And so I just got great training under Stuart. He was arguably one of the most brilliant scientists I've ever known. And then at that point, I graduated from the MD PhD program and had to choose an internship. In those days, if you were serious about science, as a physician scientist, medicine, internal medicine was really where most people went. So I decided to go into internal medicine, applied to several places, and for various reasons, went to Columbia, which was a great decision. And as I mentioned, while I was doing my clinical work, internship and residency, I became very curious about coronary vascular disease and atherosclerosis. Columbia at the time had a big unit on atherosclerosis research, and I ended up working in the lab of another brilliant scientist, Alan Tall, and that's how I learned about atherosclerosis, and that's where I decided that I was going to try to make my mark in a relatively new area at the time, which was to understand the role of macrophages in athero. And then the rest I summarized in what I told you previously, moving on from cellular cholesterol metabolism to cell death to efferocytosis to cardiometabolic disease, and now seriously linking atherosclerosis to metabolic liver disease. And again, in each of those areas, we have areas of focus. So in atherosclerosis, we're really interested in how lesion morphology is regulated, because it's lesion morphology that affects the clinical outcome. So for example, there's a fibrous cap on lesions that either protects the lesion or gets destroyed and no longer protects the lesion. So that's my major interest in atherosclerosis, how macrophages lead to control of that protective fibrous cap, and how it goes wrong. And in liver fibrosis, and in MASH, as I said, our major interest is in liver fibrosis. And that involves a fibroblastic cell type called the hepatic stellate cell. So again, crosstalk between macrophages and hepatic stellate cells and how all that is occurring.
Thank you. And could you highlight a project or discovery you're particularly proud of?
Yeah, so I think that probably the big picture that we're most proud of is appreciating how efferocytosis is linked to this repair process called inflammation resolution. Like all work, it was based upon previous work. There were some real pioneers in the area of efferocytosis, such as Peter Henson, and then Cody Radhachandran was one of the disciples that came out of that topic and really did an amazing job. And then I worked in this area. But why is it that taking up dead cells would fundamentally reprogram the cells? I mean, it's a perfect lesson of nature, right? So you have an inflammatory lesion where, for example, you get infected, right? And you got to kill the bacteria or else you'll die. So in order to kill the bacteria, you got to really put in an inflammatory response so that they're all dead. But if you do that, then you're going to destroy host tissue. You can't have both, right? In order to do a good job of killing all the bacteria, you're going to have collateral damage. Now, part of the inflammatory response is you put in all these cells that eventually die, like neutrophils. So now you're left with two problems. Nature, is left with two problems: dead cells and tissue in need of repair. So in one fell swoop, you do both. You correct both. You clear the dead cells by efferocytosis, and that very act reprograms the macrophages to carry out tissue repair. It's just a gorgeous example of nature. So we have done a lot in the area to really push that concept forward. And most importantly, number one, to understand the precise cellular mechanisms whereby that occurs. And it involves signaling mechanisms that are driven by the very cargo of the dead cells. So the dead cell is taken up by the macrophage. All of the components are degraded in phagolysosomes. That leads to amino acids, nucleic acids, lipids. They get into the cytoplasm of the macrophage, often in regulated manner. And then those molecules trigger signaling pathways that lead to the reprogramming of the macrophages to lead to repair processes. For example, synthesis and secretion of interleukin 10, synthesis and secretion of TGF beta 1, stimulation of regulatory T cells, and it goes on and on and on. So we spent many, many years and published many papers understanding how that occurs. So that was number one. Number two, understanding its importance in vivo. So setting up a lot of disease models where we could either inhibit or enhance that process and then show that it really is important. And number three, gaining more and more human evidence through the analysis of human tissue and also through human genetics. So I think that that's what our lab has done a really good job at. And now we've started to open up that field in MASH as well. And now it's been about 10 years that we've been in the MASH field. And I think that that people appreciate the work we've done there as well. And then I'm hopeful that the next big breakthrough will come through our therapy work.
Okay, thank you. And one question about the translational science or industry. How do you see the field of immunometabolism contributing to the development of new therapeutic strategies?
Yeah, I mean, that question, as I'm sure you know, goes far beyond what we're doing, although the application of what we're doing is sort of like the odd man out. I mean, you think about cancer and you think about autoimmune diseases, right? Those are the first two that come to mind. And there's been tremendous successes in both of those areas based upon immunometabolism. The fact that we can even have a discussion about diseases other than cancer and autoimmunity, where this could be incredibly important, is really interesting and talks to, the evolutionary role of immune cells beyond typical inflammatory reactions, etc. I think the deeper we understand mechanism, the better we can understand how to design drugs that are effective and safe, right? The number one reason why drugs fail is efficacy, and the number two reason they fail is safety, right? And I think a lot of the problem is not understanding mechanism clearly enough, not to mention the fact that the preclinical models that are available to us are less than perfect and often not predictive of what happens in man. That's getting better and better in the sense that, with the advent of organoids and spheroids, iPSC cells from people, that we can do a little bit of better job of bridging to humans. In certain areas, non-human primate work can help to do that. But there are advances being made more and more to try to bridge the gap between promising preclinical studies and clinical studies. And I think, as the artificial intelligent models get better and better, that's going to be a big help in this area. It already is, but it's just literally, it's almost week by week. And we are taking advantage of it as much as possible in our laboratory in order to, try to inform what we do. So that's a big part of where we're at right now is testing out various agentic models and trying to have that as a partner in our research. So hopefully that will help as well.
Well, about the impact on society, do you engage science communication activity? What's your opinion about this part of science, like show your results in Congress or your seminars or another activities?
Yeah, I think that certainly uh, at the very basic level, communication is everything. My own area of um, practice is mostly communicating to the scientific community, and I try to do as good a job as I can do on that by making myself available for talks and phone calls and emails. Clearly, getting our work out in papers as soon as possible without holding anything back. Um, Communicating with pharma and biotech is a big part of that. Um, and then certainly in terms of dealing with the community, I'm always open to that. I have colleagues of mine um, who focus on that more directly than I do, but I spend time talking with them and communicating my thoughts, perhaps a little bit of advice here and there. I see that as extraordinarily important, and I'm very, very supportive of it.
Okay, perfect. And okay, we'd like to turn now to your career journey and the experience that have shaped it. So, building a scientific career often comes with both opportunities and challenge. So, what strategies have helped you to navigate in difficult moments?
Yeah, I think that ultimately, if you love something um, and you're passionate about it, it gives you the armamentarium to push through tough times. I think that that's the fundamental layer. You gotta absolutely love it, and you have to sort of um, incorporate that you can't see yourself doing anything else. So if a problem arises, it's not like, well, maybe I should consider another career or something else, but rather, how are we going to get through this, right? So I think that by far the foundation is the passion and the love for what you do, right? And then once you have the will, then it's a matter of being persistent, hardworking, and creative to come up with the means. And that can take all sorts of forms. Um, we all are dependent on grant support in order to do what we love. That can present challenges. Um, the one of the ways of dealing with that challenge is just to work harder. Try to continue to do the best work you can do. Try to continue to get papers out so that you can support your research grants. Think, read, discuss, take it very seriously. Write more grants than you think is necessary and that you particularly want to do, but just shots on goal. A good analogy now that we're going to be heading into the World Cup in America. Something that I'm sure you're all interested in. And persistence and hard work. Uh, Obviously, luck comes in, but luck is there for people who are receptive to it, and who are there to accept it. I think that those are the strategies to try to get through the tough times.
Okay, perfect. And do you remember any decision you initially doubt that turned out to the right choice?
Well, I think that as a scientist, progresses throughout their career, um, they're constantly making really important decisions about what to pursue and not to pursue. Now, I mean, in my case, you could go back and say, well, the first decision was to get involved in research in the first place. Um, but that was really driven by curiosity. And then the second decision was whether to go to an MD PhD program or a PhD program. And I chose the former, and I'm really glad I did that because I love to think about my basic translational works in the setting of disease. And PhDs can do that quite well, but it's just not the same as if you've been at the bedside of patients suffering with the disease, right? So that was a decision to go to MD PhD program. And then the next big decision was to get involved in atherosclerosis research in general, and then sort of adapt the macrophage as my cell type. And then the next decision was to open up an entirely new element of my lab dealing with metabolic disease, because I had never done that before, right? So it was basically the liver, the hepatocyte, the hepatic stellate cell, and understanding models of metabolic disease, insulin resistance, obesity. And for that, great postdocs I brought into the lab in the metabolic case, a superstar by the name of Lali Oskan, who's now independent faculty at Columbia, was what got me through that decision-making process. And then at a more detailed level, making decisions about what to pursue. If I was interested in macrophages, there could have been a million things that I did. And the progression from cholesterol metabolism to cell death to efferocytosis were decisions along the way. And the decision to really sink deep into efferocytosis and then into inflammation resolution was probably the most important decision I made, right? And I don't remember the day that I was sitting at my desk and I said, "Hey, I'm going to work on this," but it's more of an evolution. So you're always making important decisions about what not to do and what to do, and you hope you make good decisions.
How do you build and lead a successful research group?
Yeah. So the first aspect is to understand people. If you don't understand people, it's really hard to succeed. So in the beginning, when I was young and had not done anything, I did the best that I could do to bring in the best people, both scientifically and personality wise. Sometimes I succeeded, sometimes I failed. But as I began to um, become more successful in my research, I had more choices. And I decided early on that nobody was going to come to my lab without my spending many, many days, often weeks, interviewing that person, interviewing the people that knew them, their mentors, um, and making a decision about whether to bring them into my group based not only upon um, their skills and their knowledge and their passion for research, but also their personality. And, occasionally I learned some hard lessons, but luckily those were early on and I didn't repeat my mistakes. And by doing that, not only did I bring in good scientists, but people that had the personality where they were persistent and did not get too down when things got tough and interacted well with each other and were hardworking and passionate because that's who they were, not because I told them to do it. And then that left me with an obligation to really care about them. I mean, they're my second family. I mean, I've got my wife, my son, and now my grandkids. But my lab is my second family, and they depend upon me. And I take my obligations to them extraordinarily seriously, and they know that. So it's a two-way street in leadership, right? That I am demanding, but I expect a lot of myself from myself to help them. Um, I'm very organized, and I try to find the right balance between not micromanaging, but not being aloof. So there's a bell-shaped curve, and I want to be in the sweet spot of the bell-shaped curve, right? Not stand over them, but not, be away all the time, right? So to be there third. So I've worked out a system to try to do that. Is it perfect? Of course not, but it's worked. We've had a lot of successes in getting people faculty positions. I think we're up to now 8 now, really over the last 15 years or maybe 20 years of people that are now leading assistant, associate, or full professors with multiple R01 grants in some of the leading places in the US. Very, very proud of that. You need to read people. You need to know who people are. And over the years, after having made lots of mistakes, I've honed my skills on understanding people. And so that helped me bring the right mix into the laboratory. And then it becomes self-perpetuating, right? You put a bunch of good people together, and then it becomes self-amplifying. And then, so yeah, I would say those are my basic principles.
What helps maintain a positive and collaborative lab environment for you? It just that this treat your your students or your trainees as a family, or there is other tips or?
Yeah, I mean, it begins with my own excitement and passion. I'm like a little boy in the lab. I'm jumping for joy and telling everybody, the concept of gratitude. I said, do you guys know how lucky we are? Right? Every day you wake up, you get out of bed, you get to do new things, right? I mean, think about all the choices in life. So instilling a sense of gratitude, I literally, often several times a week, try to instill a sense of how lucky we all are. And then excitement, passion. I'm not sure. I think that to a large extent is part of my personality. I'm not sure I force it. I think it's just there. And that goes a long way. And then along with everything else is that they know I really care about them, and they know I go to bat for them. And that takes a lot of hard work on my end, but it's what I do.
What qualities do you value most when you mentoring students or trainees?
Um, I value uh, passion and appreciation for what we're doing. I value independence, nothing robotic. I tell people the first day in the lab when they join my lab that every time they disagree with me, that is a great thing. And some of my people come from cultures where you never disagree with the head honcho. And it often takes me months or more to break that habit. So I reward people when they disagree with me. I super reward them when they prove I'm wrong. So I value that in people. Professionalism, hard work, taking things seriously. We all make mistakes, but trying not to make them twice or 3 times. Those would be some, and just being a good person, right? But it all goes together, right? It all goes together.
I have a little curiosity. In your opinion, what qualities make a young researcher stand out?
So I think somebody who is willing to think in an unbiased manner, to be creative, to be disruptive when being disruptive is needed and appropriate. It's a balance between not discarding everything that came before, because some of what came before might actually be valuable, but not just drinking from the same Kool-Aid container, and being courageous and bold to go off in new directions, and to buck the trend if it's appropriate, but not to buck the trend because bucking the trend is a good thing, but because it's appropriate scientifically. And somebody that is honest and authentic and is open and not secretive and not worrying about getting scooped all the time, and is generous with reagents, with ideas, things like that.
Okay, perfect. What non-scientific skills have been most important in your career? Besides that, be a good person and the other thing.
I mean, I think, as I said, it didn't come automatically in the beginning, but understanding people, I think, is probably the most important skill, actually. And to be able to read people quickly and accurately. There's just nothing like that. And trying to be authentic, trying to be real. If you're not modest, you're not being real, because the very nature of research is modest. Sometimes when I come across as modest, people say, well, it's false modesty. I say, no, it's true, because if you're a researcher, you have to be modest, because you're overwhelmed with the enormity and the complexity of science. So if you're full of yourself, then automatically that indicates something is really terribly wrong. So, these are the sorts of things that, I've grown to appreciate over the years.
What advice would you give to someone just starting in this field?
Yeah, my advice would be to make sure you're driven by the right motivation, which is passion for research, curiosity, ultimately wanting to help people, society, but it ultimately is driven by your own passion and curiosity. And to understand, like anything else that you do, that there's going to be rough spots, but to have the build up, be willing to take the time to build up skills and knowledge. Power through strength, power through knowledge, and to be persistent and to be positive. And if you feel that you fit those sorts of attributes, you've got to have a certain number of smarts, but you don't have to be a genius. I've never considered myself anything close to that. Then I think you have what it takes to really pursue a career in research. So get to know yourself, look in the mirror. As Michael Jackson said, man in the mirror. Everybody should listen to Michael Jackson's Man in the Mirror, right?
Okay. Yeah.
Look in the mirror, and are you the type of person that, because of your passion and your curiosity, and natural diligence and enthusiasm, can lead to what you want to do and be persistent and go through some of the hard times.
Okay. And what challenges or opportunities do you see for the next generation of scientists?
Oh, I think that there are so many exciting opportunities that are going to come about, many of which are centered around all the advances in agentic AI, and then onward from there. I mean, by the time the young scientists of today are moving forward, quantum chips are going to be available, and that's going to completely change the nature I mean, what we're doing now in agentic AI is going to seem just so incredibly primitive when the quantum chips become available. And there's a long way to go for that. But that's going to happen. And then it's not a matter of all of these extra tools replacing scientists. And there have been many articles written about why that's unlikely to occur. But rather, the scientists of the future is going to have incredible partners and opportunities to move quicker and better and faster, particularly as it goes from moving from basic ideas through mechanism preclinical to humans and to actual usefulness of creating new therapies. So that's going to be such an exciting area for the new generation that's going to evolve very quickly. And our field is going to look very different 10 years from 5 years from now, very different. And 10 years from now, it'll be almost unrecognizable. But if anything, more exciting. So I envy people who are just beginning now, because it's just that there's no limit to what's going to be doable.
To finish, could you share a memorable moment from your career research? Maybe something that stay with you is a positive or challenging, or I don't know, any story?
Our first discovery of how efferocytosis is linked to resolution through recycling of cargo. It was a story that was led by a postdoc in my lab by the name of Art Yurgadal, and it involved the amino acid arginine. That was just super, super exciting for us to understand that efferocytosis was more than just getting rid of dead cells, right? And understanding that when a macrophage eats a dead cell, that it's not just garbage, but it recycles it for a really important purpose. So I'll never forget that as a major move forward. And then when we first appreciated that we could start to translate our findings into novel types of drugs, and our first startup, which was in the area of insulin resistance, which is still going on, but then more recently our startup in the idea of being able to treat cardiometabolic disease based upon a common cellular pathophysiology, and that being looked at enthusiastically by investors, by venture capital, biomedical venture capital investors, and then the funding of that moving forward in that. So those are the real exciting sort of jumps in the career that immediately come to mind.
Okay, thank you. That's a wrap for today's episode of Climbing the Human Ladder, Step for Success in Science. A big thank you to Ira Tabas for sharing his insight and experience with us today. We really hope you enjoyed this conversation as much as we did. If you like this episode, don't forget to tune in next time and share it with anyone who may find it interesting. You can also follow us on our webpage to stay updated on future episodes and the last news in immunity. Thank you for listening, and remember, persistence and asking the right question are what drives science and maybe your own journey too. Until next time, stay curious.